Hello everyone, let's start. Let's continue with exercise number 5. No, not 5 but 9. Let me check here. Yeah, this is exercise number 9. So it says that we have a convex polygon and each of the vertices is colored with one color, and we have 3 colors, right? And every color is used. And okay, so let me write it. So we have a convex polygon. The vertices are colored in 3 colors such that no adjacent vertices are of the same color. Right? And we have to prove that it's possible to triangulate the polygon. So prove that it's possible to triangulate the polygon in a way that there will be all 3 colors in each triangle, in a way that there will be all 3 colors in each triangle. Okay, the first thing we have to discuss here are the definitions of what's a polygon, what's a convex polygon, what are, I don't know, the vertices of a polygon. I don't know if you know that. So what else? And what triangulation. Okay, so first of all, so polygon. I'm going to write this because I don't know if all of you know this. So let me write this. So this is a plane figure with at least three sides, right? So we have that, we have triangles, rectangles, and so on. So this is just like anything like this, or this, or like this, right? I don't know. Just so we have these sides, and the vertices are called these points here, right? These are called the vertices of the polygon. And but we are not talking just about polygons. We are talking about convex polygons. And convex polygon, and in general a convex set, but just convex polygon, it's that any segment joining 2 points inside the polygon is completely contained in the polygon. So if we have this triangle, for example, this polygon, and we take 2 points, any 2 points inside this polygon, and we draw a line between them, then all the points, all these lines must be inside the polygon itself. So what if, for example, we take a point from here and a point from here? If we draw a line, then we see that there are some points. These points are not inside the polygon. It means that this is not a convex polygon, okay? And this is not a convex polygon as well. So we can also say that a convex polygon is a polygon such that if we draw a line crossing this polygon, then it must intersect. So for every line that is crossing this polygon, it must intersect only twice the side of the polygon, okay? The side. So this is a polygon. I mean, this is like something like this, right? So, and every line must intersect only twice, okay? In this case, for example, is how many times? 1, 2, 3, 4, 5, right? 4. So that's it. So this is a convex polygon. Now we have the definition of a polygon. We have the definition of a convex polygon, and we have to ask what triangulation is. So if we have, so we have to divide somehow the polygon into triangles, okay? But so we have to we can use only diagonals to doing that. So we can, for example, doing this here and this here, right? Then we got 1 triangle here, 2 and 3 triangles. So we have to form triangles, non-intersecting triangles, but we can use only diagonals, okay? And then, for example, if we have this, so this is a convex polygon, and we can do the following, right? This and this and this, okay? And we have 1 triangle here, another triangle here, 3 and 4, okay? That's it. So this is the meaning of a triangulation. Now, next, we say that all the vertices are colored, okay? So it means that so we have 3 colors: 0, 1, and 2, okay? 0, 1, and 2 represents black, I don't know, red and blue. It doesn't matter. We can just put 0, 1, and 2, and then we can color each of these vertices here, such that no, if I have here 0, then this must be 1, okay? And this 1 or 2, and this must be 1 or 2. So let's write here 2, and then here 0, and here 1, and here 2 again. So we have this polygon, and we color the vertices in 3 colors, and we see that we have this triangulation here, such that each vertex has a different color for each triangle, okay? So that's what we need to prove, that for any possible polygon, we can do that, okay? And of course, we are going to do it by induction. Yeah. So we are going to prove this by induction, okay? But by induction on what? Well, of course, we have to consider the number of vertices or the number of sides, right? I mean, if we have how many I have here? 1, 2, 3, 4, 5, and 6. We have 6 vertices as well as 6 sides. Okay, so my induction on the number of vertices n. Okay, then the basic step is for n equals 3. In this case, we have a triangle, and then of course the condition holds for this case, right? So we can 0, 1, and 2. The triangulation is the triangle itself, right? It's the only possible triangulation here. So for n equals 3, the condition holds. Now, inductive step. Now look, we have to, what kind of induction do we need to use here? So remember, we have different kind of induction. All of them are equivalent, but they are different. Okay, so in this case we are going to use the strong. So let's use the strong inductive principle. So if you remember what the strong inductive principle is that if the condition holds, not only so, in the mathematical inductive principle is that if it holds for n, then it holds for n plus 1. Okay, when we have the strong inductive principle, it means that if it holds for 1, 2, 3, 4, 5, and so on until n, then it holds for n plus 1. Okay, so there's a, this is why it's called strong. Okay, because we are not considering only the n step here, but all the previous one. Okay, and then we have to use this. Why? Look, so let's assume that let me write that over here. So let's assume that the condition holds. The condition holds for all m less than n. Okay, so here we are going to prove it for n greater than 3. Okay, for any n greater than 3, and then we are going to assume that the condition holds for all m less than n. Okay, so what do we need to do here? So we have, let's say that this is a convex polygon. Well, this is not convex actually, so let me, yeah, something like that. So this is convex polygon. Okay, in general case, some convex polygon, and we have here the vertices, some vertices, right? What I want to do is, so, and this is the convex polygon on n vertices. I want to show that the condition holds for this convex polygon, so that if I know that all the vertices of this convex polygon are colored in 3 different colors, such that no joining vertices has the same color, then I can triangulate this in such way that all the triangles has different colors. Okay, such that each triangle has vertices with all the 3 colors. Okay, so what I want to do is I want to if I have here, for example, 0. Let me. This is on n vertices. I have here this vertex x is colored with color 0, okay? And I want to draw a line here to join this vertex with a vertex colored with a different color. Let's say with 1, okay? So I want to do this, but how do I know that this is possible? So I have to prove that I can always find a diagonal such that each vertex has a different color. Okay, so I mean this is quite of maybe this is obvious, but anyway we have to prove it. Okay, so call this some kind of lemma or something, I don't know. So for n greater than 4, because if we have 4 then this is a rectangle. In that case it's not possible, right? For n greater than 4 we can find a diagonal with different colors. So that the vertices of this diagonal has a different color. Okay, then okay, so how are we going to prove this? So let me prove this one here. So this is the proof of this lemma here. Okay, let me assume that I have any convex polygon. Then let's draw a triangle here. Okay, and this triangle has colors 0, 1, and 2. Okay, and then if I assume that this is not true, I assume that it's not possible to find such diagonal with different colors, and then I say that let's assume that this is true. It means that if I have this polygon here, and since I know that all the 3 colors are present, then I can draw this triangle here, right? Because I know that color 0, 1, and 2 are present. So I can draw this triangle. And now this diagonal here, if this is not a diagonal, then it has to be a side. Okay, so the only option that we have for this to not be diagonals, if and only if this polygon is a triangle itself. Okay, otherwise this thing here, each of these diagonals is going to be a diagonal, right? And it's going to have 2 different colors. Okay, so it means that this is true, that I can always find a diagonal with 2 different colors. Okay, and that's it. So this is the proof that I can always find. So if I have this condition that I have 3 colors, then I can always find a diagonal with different colors. Good. So I can do this. I can find the diagonal 0 and 1. Now, since I know that I have 3 colors, then let's suppose that here I have color 2, and here I have some vertex with color 2. Okay? Then, by the induction hypothesis, so by induction hypothesis, we know that here there's a polygon on, so let's call this polygon A, and here we have a polygon B, so this is a polygon B, and so A has m sub A number of vertices, and B has m sub B number of vertices. And we know that MA is less than N and MB is less than N. It means that the condition holds for polygons A and B. So for this polygon here, I can find some triangulation, and for this polygon here B, I can find also some triangulation. I don't know, right? Such that the condition holds here and the condition holds here. It means that the condition holds for all the polygon itself. Okay? Good. We proved almost everything. Now, but here we assume that we have the color number 2 in both sides. Okay? So we have color number 2 here and color number 2 here. Now, what if we have color number 2 only in one side? Then so let's suppose, so this is case 1. And this is going to be case number 2. So in this case, we have this polygon here. We have 0 and 1. We have the diagonal here. But we have color number 2 just here, not here. Okay, that's possible, of course. What do we need to do now? So we know that here, so we have here A and B, right? Then means that B has vertices, only vertices 0 and 1. It doesn't have any vertex with color 2. Then then here the vertex has to be 1, and here has to be 0. Okay? And these are different, of course. And now what do we have to do? All we have to do is to draw this diagonal here between these 2 and this 0. Okay? And it means that we obtain two new polygons here. This is going to be B prime, this is going to be A prime. And now I have this case, right? Because I have 0 and 2 dividing this polygon, and I have the color 1 here, and I have the color 1 here. Then I only have to apply this. So apply the same that for case 1, but with A prime and B prime. And that's it. It's proven. Okay, so I know that it's a, I mean, in many books the proof is not so long. I mean, the proof is just that you have this polygon here in n vertices, and then you can, or no, that you have this, yes, you have this in n plus 1 vertices, and you have this, I don't know, 0 and 1, and then you can just draw a diagonal here, and then by induction here the condition holds, and then we can just draw this vertex here by 2, and then the condition holds. This is not enough, right? Because we had to prove many things, right? We had to prove that we can actually find this. We had to prove that, we had to prove that this works for any polygon. So in this case, we have some fixed polygon. What if we don't have a fixed polygon? We have to do this for any polygon, and that's what we did here. Okay, and that's it. Because I mean, you can triangulate any polygon, yes, but you can do it in such way that each of the triangles has a different color. That's another question, you know. That's what we proved here. So it's not that trivial. Okay, so let's move forward. Yeah. A triangle can have what? Yeah, one. What about the others? Yeah, I mean, you can find such triangle, yes. So if you have any polygon with this condition, you can find a triangle at least with 3 colors. What about the others? How can you prove that all these triangles here are going to be such that this holds also? No. Okay, what if we have here 0, and we have here 0, and we have here 1. How are you going to show that in this case you cannot, and this is possible, right? 0, 1, and 0, it works, but here you cannot construct such triangle, right? Okay, so now we have to prove that we have to do exercise number 10. Now, okay, number 10. let me find it. So each member of a parliament has no more than 3 enemies in the chamber. Okay, so we have members of the parliament. Let's call them MP. It's a member of the parliament. And so for all MP, MP has no more than 3 enemies, right? Enemies? Yes. Prove that it's possible to divide the chamber into 2 factions so that each MP will have no more than 1 enemy on his faction. So we have some group of people. We have a parliament, right? With a group of people. And we know that each of them has some enemies, or maybe doesn't have, but does. I don't think that that's possible. So, but we know that each of them has at most 3 enemies. Okay, so each, if I have some MP here, some member here, then let's say that this is enemy with this one, and with this one. Okay, that's it. At maximum, it has 3 enemies. And now we have this group of members here. I have to divide it into 2 groups, such that in each group, each member has at most 1 enemy. Okay. Now, how am I going to do this? By induction, yes, but what kind of, right? So let's prove it. Let's prove it. First of all, let's imagine that we have, let's call this is the member A, right? So this is a person, a member parliament here. And we say that, let's suppose that B is his enemy. Okay, so we are going to do it that way. So we are going to, so imagine that we have here a vertex, and we are joining these 2 vertices if A is the enemy of B. And if A is the enemy of B, then we are going to understand that B is the enemy of A as well, right? And we also know that A is not an enemy of himself. Okay, so this is not possible, right? So A can be enemy of B. And yes, so we are going to construct here a graph, right? So what's a graph? A graph is a collection, a set of vertices and edges. Okay, but I'm not going to define what a graph is right now, but this is a graph. So we have some vertices. Each vertex will be a member of the parliament, and each edge here will be will denote that A is the enemy of B. Okay, and now okay, now let's okay. So let's just take, for example, this case. What are we going to do? We are going to divide the parliament is just 2 groups, any 2 groups. Okay, so we have a fixed so we have fixed 2 groups. Group called this A and B. Okay, and now in each of these groups, I have some members and some members here, right? And I'm going to say that a member, for example, a member V, so this V is bad, or yeah, it's bad if B has more than one enemy in his side. Okay, so we have two options for B to be bad. So we have either that this, right? So we have that B has three enemies here in his side, right? And we have also the case when, so let me use this. We have also the case in which so this is case 1 and this is case 2. So we have the case when V has two enemies here and one enemy here. So in this case and in this case, B is bad because it has more than one enemy in his side. So B has two enemies here in his side and three enemies here in his side. Okay, so and this is case 2, right? Case 2 and case 1. What are we going to do? So we have these fixed groups A and B. Now we have to change it. We have to change them step by step, right? We have to change these sets, trying to take all the V, all the members, bad members, and make them good. So to change them into a group in which they don't have more than one enemy. Okay, so in this case, V, let me write it here. We can change B here. So let's take this B, this member, and put it here. Okay, so here we will have the new V. B will be here, and then of course the enemies will be the enemies, so that doesn't change. But now V is good, right? Because it doesn't have any enemies here. In this case, we have also to change B here. And actually, we have two more cases. So let's call this W, right? And then one enemy of W is V. And what if we assume that W is good at the beginning? Then it has at most one enemy here. So it has, for example, this enemy. Let's call it, I don't know, Y. Okay. Yes. So this is going to be one case, and the other case, let me do that here. We have this V with 1 and 2, omega, and Y is here. So in one case, we take this V into the set A, and then we see that V now is good, right? But W now is bad because W had only one enemy, but now it has two enemies. Okay, in this case, but in this case, W had two enemies, these two enemies. We change V, and then yeah, and then we kept this like this. Okay. Wait. Yes, but so what if f factor 3? So it was good. It has only one. It has only one enemy here. It can has well, actually, it's the same case. Yeah, it's the same case because we can have also some enemy here, and then it will be a bad. Let's call this, I don't know, X. So let's just work with this one. It's the same, right? W will be bad still. So then we will have to change W back. Anyway, we have then case, this is the first case, the second case. And we have to do this procedure for many times. So we have any time that, so at the beginning we fix B and A, then we have to locate here all the bad members. We have to change each of them one by one until we obtain the groups A and B that we want. Okay, and then we are going to, so the induction will be on the number of inside edges. Now we can check what is what's an inside edge. These two are inside edge. So if we have an edge that is crossing from one group from the other, so from B to W or from W here to Y, so this edge and this edge is not an inside edge. Okay, only these edges are inside edges. And we can see that every time, so since we have only two options, we have every time we have only two options, then we can see that this number of inside edges will decrease. How? Here, for example, we have how many inside edges? We have 3 inside edges here, and then we have -3. So at the end we will have -3 inside edges because all these inside edges become non-inside edges, right? So we have 3 here, -3 inside edges. And in this case, we have how many? 2, right? And then, okay, so we add 1. So we have 2, but we need to add, so we add plus 1 inside edge, but this is -2. So this, we had these 2 here inside, and then they are not inside anymore, and we have a new inside edge here. So -2 plus 1, -1. So we have that, in this case we have -1 inside edge, and in this case we have -3. So each time in each step the number of inside edges decrease. Now then I can conclude that conclusion, and this is because of the least number principle. So this is a consequence of the least number principle. There is a final step. So because of the least number principle, and since I know that this number of members here is finite, I know that this decreasing number cannot go forever. So there will be some step
in AB,
which is going to be the last, right? And this last step, we will have obtained the division of A and B that we want. Okay, so consequence here, consequence. In the last step, we will obtain the desired groups A and B. So two groups in which each of these vertices has only one vertex inside his group, such that they are joined. Okay, so that each member has at most one enemy on his group. Okay, and that's it. So again, here it's very important that the number of members is finite. Okay, so if we have an infinite number, then of course we cannot apply this, right? But since we know that this is, I don't know, 10, 40, 60, how many members are in any parliament, I don't know, 100, then we know that somehow there will be some last step, okay? And in this last step, we will have obtained the desired A and B. That's it. Good. Next, so we finish with induction. That's very good. Now we have to talk about sets. We have to talk about sets. So first question, what is a set, right? So sets. And I'm sure that you already know this, but everything is a set. So that's the first thing that we have to know. Everything is a set. Somehow, you know, these are just words. Everything is a set. So even if you have, for example, the set of natural numbers, and you have that, I don't know, 1 is a natural number, but 1 is not only a number, 1 is a set as well, okay? And everything is a set. Good. That's the first thing that we need to know. Now, it's not possible, so for us, for all x, x cannot contain x. So this, we have to take this into account always, okay? So no set can be contained by itself, okay? This is a rule. And we obtain this from the axiom of foundation, right? Yes. And actually this say that this kind of x containing y containing so that this is not possible as well. This chain, infinite chain, chain is not possible as well. So this is not possible, and this is not possible as well. Now, because of the axiom, so let me write this into a formal way. So for all x, if x is non-empty, then there exists y such that y belongs to, now there exists z such that z belongs to y. Then z belongs to x. So this is the statement of the axiom of foundation. Okay. What is written here is that if I have some set x and x is non-empty, so if there exists some w such that w is an element of x, so if I have some set x, some non-empty set x, then if I have that, should write x, right? Wait. Yeah, something wrong here. I have for x such that is non-empty, then there exists y such that y belongs to x. Now, yeah, it's correct. And for all z, continue here, such that z belongs to y, then doesn't hold that z belongs to x. Now it's correct. So what is written here? Again, I have the set x, non-empty set x, and then I say that there exists some y that it's an element of x. So I have some y. Yeah, so I have some x here, and then I have some y here. And I say that somehow y belongs to x, right? So there exists some y such that it's an element of x. And then for any element of y, this cannot be an element of x. So if I have that, this is an element of y, right? Then this is not possible. Okay? So don't forget. Huh? Look, everything is a set. So even an element is a set. Okay? So, and a set can be element of another set. Okay? And a set can be a subset of another set. Okay? So we have this, that this is not possible. Okay? So we have two things that are not possible. This is not possible for us. This is forbidden for us. And this is forbidden as well. And we actually don't know what the set is. We just did the same that we did for all the other things in this course. I'm going to understand how we can build, how we can construct these things called sets. Okay, but we don't give any formal definition of a set. Just how. So that is why this is called an axiomatic theory, set theory, because we just give some axioms on how to build these sets. Okay, now we have this. Good. This is all the theory that we need by now. Well, actually, a bit more. All right. Yes? Yeah, okay. Once. But that's not questions for me. Excuse me, but if it's gonna, when M isn't a limit point, that's, no. That's calculus, I think. Okay. Yes. Where is W? Well, W just, in this case, we say that this is the same of saying that X is not empty. Okay, so we want to say that if X is not empty, then this holds, right? And we're going to write that X is not empty in this way, that there exists some element in X. So that's the only thing that we have to do with W, okay? Now we can't, and finally, let me write that two sets are equal by definition, if and only if this is by definition. For all W such that W belongs to X, if and only if W belongs to Y. Okay, and so here we say that X and Y are equal sets. And now X is a subset of Y if and only if the following holds. For all W such that W is a set of X, then W is a set of Y. So here we have implication, and here we have if and only if, okay? Look the difference here. And by now, that's all we need. Now, exercise number 1. Prove that we have that A is a subset of B, and the B equals C, then A is a subset of C. So we have to prove this. A is a subset of B, B is equal to C, and then this holds. Look, for any of these proof, we are not going to use Venn diagrams, okay, or anything like that. So don't do that right now. I mean, you can do that for yourself if you want to understand this, of course, because I do it myself. Like I have to draw this to understand, like, is this true or not? No. And so. But if you want to prove something, don't do this because this is not a proof, okay? How can there be an element of Y and not an element of X? Where? Well, by definition. That's the deal here. So think of an example. You will not find. This is not possible, okay? This is not possible by definition. Why? I mean, this follows from this. I'm not going to tell you why. I mean, this you have to do this on your lecture, okay? So all this, the axiom of finality, this is the most important thing that you have to know in set theory, because from this we can construct anything, and this is a consequence of this, okay, of an axiom, right? So this is not possible, just by definition. Now, So look, how are we going to prove this? Well, there are many different ways. I mean, let's call this proof 1. When is this true? So B is equal C if and only if B is a subset of C and C is a subset of B, right? You know this from the lecture, I'm sure. Okay, so then we can write that we have that A is a subset of B and B is a subset of C. And in your lecture, you prove that from this follow that A is a subset of C. And that's it. This is the proof. I mean, this is not a very formal proof, but because you have to prove this, right? You have to prove this. But I think that you did it on your lecture. But anyway, so this is one proof here. But anyway, let me show you this with a different proof. So, and I'm going to do that in this board. So we have proof number 2 here. Okay. So we have these two conditions. Let's write just this. Okay. So let me write how I'm going to write this. One sec. So A is a subset of B if and only if for all x x belongs to A if and only if then x belongs to B, right? And we have that B is equal C if and only if for all y, let's go if y belongs to B, if and only if y belongs to C. We have this, right? Then if we apply this here, then it follows that so this is no. Okay, so we know this. Now, for all A belongs to, we have to prove what? That A is, okay. A belongs to A. So for all A such that A belongs to A, then since A is a subset of B, then A belongs to B, right? By definition. And now, so because of this. And now, since A belongs to B, for all B, if and only if, A belongs to C. So this is by this condition. So we obtain that for all A that belongs to A, A belongs to C. So A is a subset of C. Okay, and that's it. You know, so there's no more that we can prove here. That's it. So sometimes we will have to work with. So we have two different ways to prove this. We can use just the algebra of sets. So we can just do something like this, yes, or we can work with the elements of the sets. So if I want to prove that A is an element, is a subset of C, I have to prove that all the elements of A are elements of C, and that's what I did here. All the elements of A are elements of C. That's it. Now number 2. Here. No, I will need that. Oh, I think it will be fast. Number 2, which one is number 2? So we have two sets. So this is number 2. We have the set A is, let me just take it. I will write it. 1. Okay, this set. I have to tell you what are the elements of this set. So let's call this set A. This is set A. Who can tell me how many elements has this set? So this is the cardinality, right? I don't know if you already know that, but this is just the number of elements in A, the cardinality of A. So the number of elements here, how many? You can write on YouTube, right? So, and let me write B now. Yes, 3 elements. So we have that this is an element, this is an element, and this is an element here. Empty set is not an element here. It's a subset, not an element. Okay? So empty set is a subset for any set, not an element. Okay? No. Look. From here. A subset is not the same of an. So look. What is the definition of a subset? The definition of a subset is that if belongs to this, then it belongs to this. Right? Yeah. But this is different to this. These are completely different things, right? So look at this definition, and you will see it. Okay. So we have 3. One, this thing and this thing. Now, how's the name of this? What's the name of this element here? Of this set, right? Because this is an element, but this is a set. Who can tell me? Who can write there? Yes. Singleton, I don't know how it's, but singleton, let's call it. Okay, so this is, how many elements are here? in this set? 1. So 1 is an element of this set. Okay, good. What about this? How many elements are in this set here? 3. Yes. So we have 1, 2, and the singleton of 2. So tell me, 2 belongs to this element, to this set? No, because of this, right? So this is an element of this set, but 2 itself is not an element of this set. Okay, these are different things. Good. Now, well, this is done with A. What about B? So for B, we have so many elements. How many elements? 3. So we have this. We have the singleton for 0. And then we have this, right? So this is just one element, right? And tell me, 0 belongs to this element, to this set? No, okay? So the singleton of 0 belongs to this set, but not 0 itself. Okay, good. Well, and I think that's it with this. It's pretty clear. Well, okay, now number 3. Now here. So I have to construct sets such that, so let me write. So number 3 is that construct a set such that A belongs to B, B belongs to C, and A belongs to C. Who can tell me an example of this set? So look, we can draw something here. So we have that A belongs to B, and then B belongs to C, right? And A belongs to C, right? So this is not possible. So we cannot construct such sets A, B, and C. Not possible. So this is impossible. Impossible. By definition. Okay. So this is the first case. And what if we have that? What do we have? The same, but so we have that A belongs to B, and B belongs to C, and A doesn't belong to C. So we have this. A, B, and C. This belongs to this, and this belongs to this, and this doesn't belong to this. So what sets should be A, B, and C? What kind of sets? I mean, is this possible to build this? Yes, because it's possible, and that's it. So there's nothing that forbidden here for us. Now, what kind of sets should be A, B, and C? This cannot be any sets. It has to be some defined sets here. So who can write? Who can tell me? What kind of sets should be A, B and C. A, yeah, okay, yes. Now, what kind of sets cannot be B and C? Your examples works, I think, yes. But what kind of sets cannot be B and C? And A. So well, right. Who can tell me? Okay, what if A is empty? So A is equal to the empty set. Is that okay? What do you think? So who can write yes, no, what? Is it okay if A is empty? It's okay. Okay, I'm not going to ask why because, but what about if B is empty? Is it okay? No, why? Why it's not okay for B to be empty? Yes, because A belongs to B. Okay? So B cannot be empty and C cannot be empty as well. Right? That's it. A can be empty, can be anything you want. But we care about B and C. Okay? That's it. And does the empty set belong to each set? No. Or is a subset of each set? Yes. So the empty set doesn't belong to, for any set, the empty set is not an element of A. There are some cases in which it is an element. But in general, this is not true. But for all A, the empty set is a subset of A. And this is true. The empty set is always a subset of any set. And you will prove it in your lecture. Okay. Well, it's not difficult to prove, but anyway. Now we have 5 more minutes. And we have exercise 4, but exercise 4 is long. So let's just do exercise 5. And then the next class we will do exercise 4 instead. Okay, so exercise 5. By the way, do not forget that you have a new homework. And this one is long enough. So, thank you. This new homework is long, so pay attention to that. I will be listening to you. The last day will be, I don't know, about at the end of December. After December, I don't think I will be listening to more solutions. So Pay attention to that. I will write that. Okay, so number 5, and we have to finish. So we have to give an example of A and B such that A is not an element of B. So A is not an element of B, and B, wait, but A is a subset, is not a subset of B. Who can tell? Okay, couldn't I say that B is A, and in A you say, right? B is A. Wait, B is A and C is this, so it means that A is an element of B. It's about this. No, I think A, he's talking about this one, right? Right, Lucas? No? Okay, so yeah, it looks A is an element of B. Yes, and I know, but what's C? Yes, you were talking about this one. Yes, sorry. Okay, so who can tell me? We have 2 minutes. Yeah, the previous one. Who can tell me? So let's look at B. We have to find some set for which no element is, nothing is an element. So what if B is just the empty set, right? So this holds for any A. And this holds? Yes, of course, because any set, any set, any non-empty set. So if we have that, yes, it's a subset. The empty set is a subset of the empty set, because the empty set is a subset of any set, and the empty set is a set, right? So that's it. So we have to take B empty, and this holds for any A, but this holds not for any A, but for A non-empty, right? So just take B empty and A non-empty set, and that's it. You can give 100, 1,000 examples of A and B, but I want you to find the general case, right? Because you can write, I don't know, this is 1 and this is 2 and so on. Yes, but what about the general case? I think this is more interesting for us here. Okay, so in this case we have this, and in the next cases that will be for next class. Okay, I think that's it. Thank you very much.